Yeah, so there's four, so let's go ahead and talk about cards for a second. Just because might as well. So Co-17C, today is March 1st. So just some probability terminology, and anyone who is welcome to get one of these handouts from me. I think I also posted it in Canvas, so it's accessible there. So a standard deck of cards contains 52 cards. There are 4 suits: clubs, hearts, spades, and diamonds. There are 2 colors, red and black. Clubs are black, spades are black, hearts are red, diamonds are red. There's 13 ranks or values, although we usually use the word rank. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. Ace can be thought of as high or low. That's important when you're talking about a straight, because you can have a straight that starts as low as an ace. It can be ace, 2, 3, 4, 5, or you can have a straight that ends with an ace. It can be 10, Jack, Queen, King, Ace. There's 3 face cards in each suit. Jacks, queens, and kings are considered face cards. And then as far as poker goes, there's a few different kinds of hands. I'm starting from like the lowest ranking hand. And really, so it's interesting. These ranks are based on the probability of getting them. The higher value a hand has, or the better a hand is purely a function of how hard it is to get it. The harder hands to get are the ones that are worth more, that beat other hands. In fact, once upon a time, I believe a flush beat a straight up. Flush used to beat a full house. Because people didn't realize it was harder to get a full house than it was to get a flush. It's interesting. So just so you're aware, the lowest kind of hand is just no. So in a 5-card hand, because we're typically have about 5-card hands, the lowest possible thing you can have is just no pairs, no reserve kind, just high card, whatever your highest card is. Then after that, 1 pair. So you have 2 kind, and the other 3 cards don't match. Let me just change this here. Hi, Andrea. We're just talking about poker in the context that we need to know how it works with probability. And then this handout is available on Canvas, I believe, and it's also, if you want to get a physical copy of it, I'm happy to give you one if you come by my office sometime or come to office hours or whatever. So after 1 pair, then 2 different pairs is the next highest hand. So like a pair of 9s and a pair of 3s, and then a 5th card that doesn't match either one. And then you can have 3 of a kind, which is like it sounds, 3 of one kind, and then the other 2 cards don't match the 3 of a kind or each other. After that, as far as goodness of hand, is a straight. That's 5 cards in a row or in sequence. But they don't, and the suits don't matter. So it can be like 3, 4, 5, 6, 7. All different suits. I mean, not all different suits, because one of them, there's only 4 suits, but like no, the suits don't have to all be the same. Then we have a flush, which is where all the cards have the same suit, but the order or the ranks don't matter. Although, so the flush, like for example, if 2 people had a flush in poker, then the flush with the high card would be the winner. So if my flush has a high card of a jack and your flush has a high card of a king, your flush would win. Just like if my straight went higher than your straight, my straight would win. King is higher than, so the order of cards. So ace counts as low and high. So it goes ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then jack, queen, king. And then ace again.
So A is a high or low?
Correct. Ace can play high or low. The only time we usually need it to play low, or you would want it to play low, is if you're trying to make a low straight. Ace, 2, 3, 4, 5 is a straight. So is 10, jack, queen, king, ace. Other than that, there's no reason to have the ace play low. Without some, there are lots of interesting poker games. Sometimes there's like a poker game called like a high-low split, where the high hand and the low hand each take half the pot. And that might be an instance where you want an ace to play low instead of play high. After a flush, then there's a full house, which is 3 of one kind and 2 of another kind. And typically the ones that you have, so typically the way you would name that, like this one here, that's sitting in, there's 2 kings and 3 threes. You would say you had 3s full of kings. The 3 of a kind full of the 2 of a kind is how you would say that. How someone might say it to you. 4 of a kind, obvious. You have
How it's based on the pairs, right?
The 3 of a kind is the so whoever has the higher 3 of a kind has the better full house. And then 4 of a kind is what it sounds like, all 4 of one rank, and then a 5th card that obviously can't be that rank because there's only 4 of that rank. Finally, I think these two should be the same category personally, but they've written them differently here. You have a straight flush, which is all 5 cards have the same suit and they are in sequence. So you have all hearts, and it could be like 4, 5, 6, 7, 8, or all hearts, 9, 10, Jack, Queen, King. And then finally, the best hand you can get in 5-card poker without any wild cards is a royal flush, which is just a straight flush, but happens to be the highest straight flush you can have. So 10, Jack, Queen, King, Ace, all of the same suit.
But color doesn't matter, right?
Color doesn't matter typically. Yeah, there's no like all red, which there's a funny movie where, well, not funny movie. There's a movie where some guys are playing poker and they're like teaching some like Hollywood types who don't know anything how to play poker. And Topher Grace from that 70s show, you might know the main character. Okay, he's an amusing kind of nerdy actor. He lays down his card. He's like all red, and the guys are just like, yeah. So yeah, all red, not a good hand unless they're all the same suit, either all hearts or all diamonds. I don't know. Yeah, probably not. It was yeah. I think the movie is that. I think that's Rounders. Good movie. Highly recommend it. And then the other side of this, I don't want to get too much into, but we have some biology stuff. Most of the times, the biology stuff comes down to like the Punnett square kind of thing. So if you have, and I'm not great with the words here. A gene is genetic material. Forms of the gene that can occupy a given position are called alleles. There are multiple alleles. Then the specific alleles on the chromosome pair are the genotype. So like a dominant and a recessive, or 2 dominants or 2 recessives. And then the expression is the genotype. So for example, I have blue eyes, which means I have 2 recessive little b genes for my eyes, whereas people with brown eyes could have a big B, or a big B, little b. Now that's obviously dumbing down because there's lots of other stuff with eye color, but that's the basic idea. Is the dominant gene gets expressed if it's there. The recessive gene only gets expressed if it's the only one that's there. And so then you can have Punnett squares like this where you have like all the possibilities, like someone's AA like that, and then these are the 4 possibilities for their children. So you have a 1/4 possibility of your child being AA, a 1/4 possibility of being big A, well, actually no, a 2/4 possibility of being big A, little a, and then a 1/4 possibility of little a. So here there'd be a 3/4 chance of the person expressing the dominant dominant phenotype. Yeah, and there'd be a 1/4 possibility of their child expressing a recessive genotype here. And it's going to be different based on your parents, right? If you know the parents are something like this, right? If you know for sure that one parent's recessive and then one parent's dominant recessive, then you get big A, little a, big A, little a, little a, little a, little a, little a. So my wife and myself, if we had kids, she has brown eyes, but we know that there's some recessiveness, so it's pretty likely that she's a big A, little a, or a big B, little b. We would pretty likely have a 1/2 chance of having a blue-eyed child and a 1/2 chance of having a brown-eyed child. Or we're not having kids, so there you go. All right. So that said, let's look at some probability things. So we're gonna start off by talking about the multiplication principle. Oh, and I feel like that's somewhere on there too. No, I guess not. That's fine. Doesn't mean cool. So the multiplication principle. And something I'll say very generally, and I'll repeat this a lot, is when you're talking about probability, the language is very important. So if you hear something like, we want to know the likelihood of this and that happening, that usually ends up meaning we multiply the probabilities together. Whereas if we want to know the probability of like this or that happening, that typically means we add the probabilities together. But we'll get more into that as we go on. Just keep that in mind. That language piece should be helpful in kind of figuring things out. So let's look at this example. In planning your spring quarter schedule, which you should have already done, right? I mean, registration has happened. So you're gonna be taking a stats class, a bio class, a chemistry class, and a music class. We're not gonna get super specific here. We're just making stuff up. So there are 4 sections of stats. 2 sections of bio. 3 of chemistry. And 2 of music. Assuming that none of these like overlap or conflict with each other, how many different schedules could we make picking 1 stats, 1 bio, 1 chem, and 1 music class?
So we're including everything, right?
Right. So there are 4 different stats classes or sections I could choose from. Unless it like maybe like the first stats class meets Monday, Wednesday, Friday at 9, the second one Monday, Wednesday, Friday at 10, the third one Monday, Wednesday, Friday at 11. Right? They meet at times that don't overlap, so we can pick any one of the 4 of them. So we have 4 different choices for our stats class. And then for each potential choice for our stats class, we have 2 different bio sections we could pick from. So for example, we could pick the first stat section and the first bio or the second bio. We could pick the second stats and the first bio or the second bio. The third stats and the first bio or the second bio. Listen to the words I'm saying. The fourth stats and the first bio or the second bio. So we're going to have a stats class and one of the bio classes. All right, and then for each bio possibility here, we can pick one of the 3 chemistry classes. So we could pick the first section, the second section, or the third section, or first, second, or third. And this goes on, right? I don't want to write all this out because it's going to get a little messy here, but each of these would also have 3 choices, 3 choices, 3 choices, 3 choices, 3 choices, 3 choices. And then for each potential path I can take, right, branching off from every chemistry class, there's 2 music classes I could take. So the total number of schedules, or the total number of possible schedules, is the number of branches. So let's see. 1 times 2 times 3 times 2. So for this first stats one, right, there's 2 branches, and then for each of those 2 branches, there's 3 branches, so that's 6. And then for each of those 6, there's 2 more, so that's 12. But then for each stats, there's 12, so there's really 12 plus 12 plus 12 plus 12, which is 48. Or the easier way of doing this is that the number is going to be the number of sections of stats times the number of sections of bio times the number of sections of chem times the number of sections of music. Which is 4 times 2 times 3 times 2, which is 8 times 6, which is 48. So there's 48 potential schedules we could make with these numbers of choices. Okay. So this is the idea of the multiplication principle. Saying basically you have this thing and that thing and that thing. We're going to multiply our possibilities together. Let's look at another example. I'll try to write less. In a study, okay, I really don't want to write all this. In a study on the effects of light and fertilizer levels on plant growth. You don't have to write all these words, by the way, if you don't want to. We plan to study 5 different fertilizers, 3 different light levels, and we wouldn't want just one plant with each fertilizer and light level combination. By the way, at this point, how many fertilizer and light level combinations are there? Right, 15, 5 times 3. But for each fertilizer and light level combination, we want 4 plants so that we can, see some, right? Because not every plant's going to do exactly the same thing. We want to be smart in our system of testing here. We want 4 replicates for each. For each fertilizer and light level combo. So how many plants do we need? Well, 5 fertilizers and 3 light levels and 4 plants come out to 5 times 3 times 4, which is going to be 60. So we need 60 plants. And if you think about it, right, so if we think about our fertilizers, right, we have fertilizer 1, fertilizer 2, fertilizer 3, fertilizer 4, fertilizer 5. And for each fertilizer, there's 3 different light levels. So there's your 15 fertilizer and light level combos, but then for each combo, you want 4 plants. So you want 4 plants that have this fertilizer and light level, 4 that have this, 4 that have this, 4 that have that, 4 that, right? And so you have 4 for each of the 15 combinations, and 4 times 15 is 60. So that's at the very basic level what the multiplication principle is. You just take the numbers and multiply them together if you want this many of this many and this many things. It's not the easiest thing to say in words, as you can hear me saying it not well, but that's why we're giving examples, because the examples I think help make it a little bit more clear.
So in this case, there's 5 different fertilizers.
Correct.
Different lights, and for each light, there's
Correct. Exactly. And so we need to buy 60 plants. Let's look at another example. The genome. Oh, another thing you should know for biology questions is the number of nucleotides in DNA. What do we call the nucleotides in DNA? Just the letters A, C, G, and T. Right? Those. So you should be familiar with those. They come up. Remember the movie Gattaca, right? So the genome for HIV contains 9,749 nucleotides. I didn't know that. There are 4 different types: A, C, G, and T. Of nucleotides. How many genomes are possible that are this long? Okay, so very common tactic when you have a whole list and you have a number of possibilities for each kind of entry is to kind of write them out. So you're saying in the first entry, the second entry, the third entry, the fourth entry, fifth entry, all the way to the 9,748th entry, 9,749th entry. So how many choices do you have for your first nucleotide? It's not a trick question. It's what you think it is. 4. No, there's 4. A, C, T, or G. Those are the only things we can choose. A, C, T, or G. How many choices do we have for the second nucleotide? How about for the third nucleotide? Right. So each slot has 4 choices. And so the number of possible nucleotides you're going to get is 4 times 4 times 4 times 4 times 4 times 4, 9,749 times, which is going to be 4 raised to the power of 9,749. It does make sense to multiply here, right? Because if I made the question much easier, if my genome was only 2 nucleotides long, how many choices would there be? Or how many potential genomes would there be? Well, right, there's 4 choices here, there's 4 choices here. We could actually write them all out, right? AA, AC, AT, AG, or CA, CT, CG, CC, or GA, GC, GGT, or TA, TC, TG, TT. Clearly in this example, well, maybe not clearly, but in this example, the order of the nucleotides does matter, right? It's not the same if you do AT or TA. Because that's, I mean, I think that's true about DNA. The order that the nucleotides are in matters, I think. I don't know. I'm not the bio guy. Okay, what's that?
A can't bind A.
Whatever. That's, it's not binding with it. It's like it's the one half. It's like this half and then the other side is what it's binding with. We're only writing the one side, I think. I don't know. We're not worrying about it. None of the math people are going to care about your biology knowledge. Right, exactly. So ignore the biology.
The mouth.
Just do it. Just do the, yeah. Yeah, I remember there's one question that was on web work last quarter. It's like, and we really had to like figure out what the fuck was going on with biology. And it's like, what is going on? Okay, so after the multiplication principle, now we have permutations. When you hear the word permutations, the thing you should think is that order matters. So when we're talking about permutations, we're typically thinking about the number of ways of arranging some things. So the number of arrangements, and really the thing to remember here is that order is important. We care how people stand in line. For example, we care that if I'm standing in front of you or you're standing in front of me, that's a different permutation. Here are some examples. Actually, before we do some example, no, we'll do an example. Yeah, we'll talk about that. So at the library, there are 4 math books, 4 different math books, I should say. 4 different math books, 5 different chem books, 6 different biology books. How many ways can I arrange them on the shelf? All right, well, I'm usually going to think left to right unless there's a reason to think right to left. So I have 15 slots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. How many choices do I have for the book that goes in the leftmost slot? Well, I haven't put any books down yet. I've got this stack of 15 books. So how many choices do I have? 15. I could choose any one of those 15 books. Okay, I chose one. I chose one of the math books. Now, in the next slot next to it, how many books do I have to choose from now? Right. And then, right, all the way down to no one wants to write all that, so we have a notation for it. When you have 15 times, when you have a number multiplied by all the lesser integers down to 1, we write that as 15 factorial. That's what that exclamation point means. That means multiply by all the number. It's only for integers. Well, that's not true. But in this class, it's only for integers. If you write a number, a positive integer number, factorial, that means multiply by every number less than it all the way down to 1. So if I said, 4 factorial, that would be 4 times 3 times 2 times 1, which would be 24. 15 factorial is not something we should calculate. We should just leave this 15 factorial. Most calculators do have a factorial button in them somewhere, typically in a probability. In fact, do I have my calculator with me? Good question. No, oh yeah, let's see. So can you see this kind of, maybe? Sure. So if you look here in this calculator, can you kind of see that? Yeah, okay. So if I wanted to find 15 factorial, I'd do 15. And then in this calculator, you would go to the, where would you go? I thought there was a probability button here. I guess I would look in stats first. Nope, doesn't seem like it. Really thought, typically, I feel like I saw a probability. Usually there's like a probability thing. It's possible this calculator doesn't have it. Yeah, I guess not. Or it's somewhere that's hidden that I don't know where it is. Mode, no, not mode. Oh, math, the math button here. You go to the math, and then you go over to the right to probability. There's your factorial button. And then you press enter and you get a big number. Because all those numbers multiplied together is not small. We'll come back to that in a minute. Okay. What if instead I want to arrange the books so that all books of the same subject are adjacent? So let's just say we're going to do the math ones first and then the bio and then the, or biochem. Sorry, math, chem, oh my gosh, math. Let's say we're going to do math and then chem and then the bio books. So how many ways are there of arranging the 4 math books so that they're all next to each other? For 4 factorial, right? Because there's 4 choices for the first book, 3 choices for the second book, 2 for the third, and 1 choice for the last book. That's 4 factorial. Or 4 times 3 times 2 times 1. How many ways of organizing or arranging the 5 chemistry books? Right? How about the 6 bio books? Okay, but we're not done. Because we didn't have to put the math books first and the chem book second and the bio books third. So how many ways are there of arranging the order of the subjects? Not times 3, times 3 factorial. Think about it. You could either do math, chem, bio, math, bio, chem, bio, math, chem, math, bio, or math, no, not math, bio, chem, math, or bio, math, chem. Right? Order matters. These 3 things, math, chemistry, and biology, can be permuted in 3 factorial, which is equal to 6 different ways. So our final answer here would be 6 factorial times 5 factorial times 4 factorial times 3 factorial. Because for each, right, if I do math, chem, bio, then I can do that, and that. But if I did my math, bio, chem, I would do that, and then I'd switch these, and each different permutation would count as a different way of organizing the textbooks. Kind of neat. So the number of arrangements, which is not the word I would prefer to use, or permutations. It's okay, Karen. All right, no worries. Of n objects is n factorial. And this is a reminder, n factorial is equal to n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. It feels kind of silly to write the 1 because you don't really multiply by 1, but I should mention that 1 factorial is equal to 1. And this one's kind of weird, 0 factorial is also equal to 1. We'll talk about why in a little bit, maybe not today, but definitely next time, if not today. It's kind of like how 5 to the 0th power is equal to 1. We need it to be true because some other rules tell us it has to be, right? In fact, let me remind you all, why does 5 to the 0 have to equal 1? Well, because of the additive law of exponents. We know that if you, like, for example, if I said 2 to the 3rd times 2 to the 4th, you would tell me that's equal to 2 to the what? Right, 2 to the 7th, because really I have 2 times 2 times 2 times 2 times 2 times 2 times 2, and that's 7 2's multiplied together, which is 2 to the 7th. Okay, well now check this out. What's 5 to the 0th power times 5 squared? Well, what's 0 plus 2? 2. So I should have 5 squared over there, right?
I just looked at
Okay.
that.
Okay. What's 5 squared equal to? So 5 to the 0 times 25 equals 25. There's only one number that fits the bill. 5 to the 0 has to be 1. There's no other choice. Any other number times 25 wouldn't equal 25. So because we all have agreed that we want the additive law of exponents to work, we have to then agree that anything raised to the 0th power is equal to 1. And in a similar way, which we'll see in a little bit, we'll see why 0 factorial also has to equal 1. For now, I just hope, and again, we don't really run into this too much in this class, but it can come up occasionally. So 5a, how many arrangements or permutations of the letters in the word math are there? Well, there's 4 letters. They're all different. So the answer is going to be 4 factorial, which is 24. And at least once in your life, you should write out these. So let's write them out now just so we can see them. So here's how you kind of, here's how I think about writing out all the permutations in a, what's the word I'm looking for? In a systematic way, so that you're not like guessing what you need. So I'm going to start with the leftmost letter always being the same. I'm going to do M-A-T-H. And then I'm going to switch the last 2 letters. So M-A-H-T. Those are all the ones that start with M-A. So now I'm going to change the second letter to H. So M-H-A-T, M-H-T-A. All right, I'm done with M-H. Now I'm going to do M-T. M-T-A-H, M-T-H-A. Those are all the ones that start with M. So then we keep going. So you can kind of see I'm going to get 6 things for each different thing I can start with. If I start with A, I'm going to get A-M-T-H, or A-M-H-T, or A-H-M-T, or A-H-T-M, or A-T-H-M, or A-T-M-H. And I think you could finish the rest, right? You could do the ones that start with H and the ones that start with T. And so you can see that there's 6 plus 6 plus 6 plus 6, which is 24 total different permutations. Okay. What if instead I said, how many permutations of the letters in the word data, or data, depending on how you want to pronounce it? Well, now we have kind of an issue because the A's are indistinguishable from each other. So let's actually write them out. But I'm going to call one of them A1 and one of them A2. So I'm going to say I have data, DA1, TA2. And then I'm going to do just like I did before. I'm going to switch the last 2. So DA1, A2T. And then I'm going to switch. Sorry, I'm going to, oh my gosh, what am I going to do? And I'm going to put the T next. DT, A1, A2, DT, A2, A1. And then I'll finally do the A2 second. So DA2, TA1, DA2, T8, A1, T. The problem is this one here, these 2 are really the same. So I'm kind of double counting. And where else? These 2 are the same. And these 2 are the same. So in my list of 6 things, I have 3 repeats. So what's going to happen here, and we could write the rest of them, right? We could start with A1, start with A2. In fact, the ones that start with A1 and the ones that start with A2, those are the repeats of each other because you're switching the A1 to the A2 spot. And then finally, the ones that start with T, they're going to be their own list of repeats. So what we're going to do here is we're going to say, well, the number is going to be 4 factorial, but then we have to divide by 2 factorial for the double counting for each A1, A2 thing. So it's going to be 24 divided by 2, which is 12. And then we can apply that same sort of idea for other words. Like, what about the word Mississippi. MISSI Yeah,
You divide it by 2 factorial,
right,
but it just stay 2. Or would it-
right. 2 factorial is 2. Because 2 factorial is 2 times 1 and you're done. But it is, the reason I wrote 2 factorial is so that when we do it now, you'll see that we need what we need. So here, how many letters are in Mississippi? 4 plus 4 plus 4 plus 1, I think it's 13. Because there's 4, oh, sorry, no, there's 4 S's. There's 4 I's, 2 P's, and 1 M. So that's 4 plus 4 plus 2 plus 1, which is 11. So there's 11 factorial ways of arranging those letters, but we have to divide by 4 factorial ways of arranging the S's, because there's S1, S2, S3, and S4. 4 factorial ways of arranging the I's, 2 factorial ways of arranging the P's. If you really wanted, you could write a 1 factorial for the ways of arranging the M's, even though it's kind of silly. So when you have things like this, if things are repeated or indistinguishable from each other, we have to divide, by the number of ways you can rearrange them because they're kind of getting counted as the same. And we don't want to count things twice. Cool. How much time we got? Okay, we got one more. In an art contest with 10 entries, how many different ways could we award first, second, and third? So, how many choices do we have for the first prize? I think there's more. How many entries are there? Right? All 10 people submitted artwork. I could pick any one of them to be the winner because it's subjective. I'd be like, I like that one best, or I like that one best. So there's 10 possible choices for the winner of first prize. And then after I've chosen the first prize winner, how many choices are there for the second prize? And then for the third prize? Right. Which is equal to 720. I don't really care about that though. What I really actually care about is that I'm going to write this as 10 factorial divided by 7 factorial. Right? That's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 7 times 6 times 5 times 4 times 3 times 2 times 1. And all the things that cancel, and you're left with 10 times 9 times 8. Or I would actually really prefer to write this 10 factorial over 10 minus 3 factorial. And the reason I'm writing it that way is because that's kind of how the formula is described. I honestly, if someone asked me this question, I wouldn't do it this way. I would think of it as 10 times 9 times 8, but someone might present it this way, so you should see it. So the formula here that I'm going to refer to is the number of permutations of k objects from n objects is given by, and there's like 5 different ways of writing this. Some people write p of n comma k or p n k. It's equal to n factorial over n minus k factorial. Just like we had up there, 10 factorial over 10 minus 3 factorial. Here's a fun question. Maybe. How many ways are there of choosing 10? No, that's a bad question. I'm not even going to say that. But I do want to point out that there's a button for this on your calculator as well, probably. So if we want to do 10, we want to know how many ways of permuting 3 things out of 10 things, we would say 10, and then we would go back to math over to the probability, and we'd hit NPR. They use R instead of K. And then we'd hit the other value, which is 3, and we should get 720, and we do. So sometimes, I mean, they're not terrible to calculate, but sometimes they're kind of large, and if you actually want to know the number, this is an easy way to get there. A lot of the times, though, you'll just leave your answer as this, 10 factorial over 7 factorial, or whatever you've got. Okay, let's talk about combinations. Yeah, combinations. Yeah, combinations. So permutations order matters, combinations order doesn't matter. In fact, let's revisit the same question we just looked at. Same art contest, but now I want to know how many ways can I pick the top 3? How many ways can I select 3 people to be in the top without telling you who won first, second, or third? It's not quite. So how many ways can we pick 3 out of 10? 3 people out of 10 people. We're going to pick our top 3, and then later on, we're going to let someone else decide who's first, second, and third. We're just picking the top 3. Okay, well, the difference here is that last time we cared about order. So like maybe we pick persons A, B, and C to be 1, 2, and 3. Or we pick D, E, and F, or J, H, and F. But the thing is, if I pick, for example, A, B, and C to be the top 3, maybe A is top and B is second and C is third. Or maybe A is top and C is second and B is third. Maybe I have BAC or BCA or CAB or CBA. Meaning, from those top 3 people, there's literally 6 different ways I could arrange them, or 3 factorial ways I could arrange them into who's actually first, second, or third. So the difference here is that when I'm picking a specific permutation, I'm counting each of these things as being different. So when I'm just looking for the number of ways I can pick any 3 people, and I don't care about the order I pick them in, I am overcounting. If I do 10 times 9 times 8, I'm overcounting by a factor of 6. Because I'm counting each of these as different. Just like if I selected persons A, D, and F, right? I'm thinking of the people as like A, B, C, D, E, F, G, H, I, J, because that's 10 letters, right? There's 6 ways of doing that. Or if I picked D, B, and J, 6 ways of doing that. But I don't want to overcount by a factor of 6. So what we're going to do is we're going to take our 720 from before, and we're going to divide by 6. Because that's going to tell us how many ways of just picking any 3 people or choosing any 3 people. So here's what it really looks like. 720 divided by 6 is 120, by the way. But the formula for this is 10 factorial, the number of ways of arranging any 10 things divided by not just 10 minus 3 factorial, but also by 3 factorial. This part here gives us the number of permutations. And then this part here gets rid of the overcounting. We don't want to count all 6 of these permutations as different. We only want to count 1 of them. Same here and here and here and here and here. So yeah, we'll do one more and then we'll, yeah. Let me give you another example so you can kind of see this. How many permutations of, and I'm saying permutations on purpose here, right? We'll do permutations of 2 letters out of 5 letters. Well, 2, I really want to do 2. No, I want to do 3. Sorry, I want to do 3. I'm going to try and do this in the last 4 minutes here. So, if the letters are A, B, C, D, and E, I could pick the first 3 letters And then all the ways of rearranging those, which there's 6 ways, right? Just like I said before, ACB, CAB, CBA, BAC, BCA. But I could also pick A, B, and D. And there'd be 6 ways of arranging those. Or A, B, and E. And there'd be 6 ways of arranging those. I'm assuming everyone's okay with me saying the 6 ways of doing this without writing them all out. Right? I could do ADB, BAD, BDA, DAB, DBA. But I think you can see for any 3 distinct letters, there should be 6 ways, 3 factorial ways of arranging them. So now let's count up, well, let's say I had ABE. I'm done with AB something. So now let's do ACD, ACE. I'm done with AC. Now I'm going to do ADE. I'm done with AD. Let's move on to B. BCD, BCE. I'm done with BC. So I'm going to do BDE. I'm done with BD. So I'm going to do CDE. And for each of these, there are 6 ways of arranging them. And if I've done this correctly, there should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is equal to 60 ways. Not surprising, right? Because we could have just said it's 5 factorial divided by 5 minus 3 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1 over 2 factorial, which is just 2 times 1. And then those cancel, and 5 times 4 times 3 is exactly 60. And the way I've written this, we can actually see what the 10 combinations are. The 10 possible combinations of 3 letters out of 5 letters is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All 60 ways of writing them out divided by 3 factorial, the number of ways of rearranging the 3 of them so that we don't overcount by a factor of 6. So the number of combinations, or in other words, the number of ways of choosing 3 letters out of 5 without regard to order is going to be 10. It's going to be 10 factorial. Oh, sorry, I'm running out of room here. It's not 10 factorial. Don't say silly things, James. It's going to be 5 factorial divided by 2 factorial and also divided by 3 factorial. The 5 factorial with 2 factorial is again giving me the 60, and then the 3 factorial is going to do away with the overcounting. So the nice thing about this formula is that the bottom parts, the things that are being factorial, always add up to the top part. So like if I'm doing, the number of ways of picking 3 things out of 5 things, it's 5 factorial over 3 factorial, and then there's also a 2 factorial because 3 plus 2 has to be 5. So I know it's stupid, give me like 1 minute. I just want to say 2 things. So let me make sure I write this right. The number of combinations of k objects from n objects is n choose k. That's how we read it. And it's written as either, and so I'm going to tell you the right way to do it, and then I'll show you the other terrible ways of doing it. This is the right way to write this. N choose k. A big parentheses, the n over the k. There's no division line. It's just n on top of k in a tall parentheses. If you prefer, you can write it as like C of n comma k or CNK. Those are both terrible in my opinion. This is how a math person would write it. And it's equal to n factorial over n minus k factorial and also k factorial. That's the choose formula. It's also in your calculator. And now let me say the last thing I want to say, which is that let's say I asked you, how many ways of picking 10 people out of 10 people are there? If I said I have a group of 10 people and I want to know how many ways can I pick all 10 of them? One. There's only one way. I pick all 10 of them. There's only one way you can pick all the people in a group of all the people. Right. So but here's what I want you to see. So if I want to know what 10 choose 10 is, it's going to be 10 factorial over 10 minus 10 factorial times 10 factorial. The 10 factorials cancel. I'm left with 1 over what? 0 factorial. And this is why 0 factorial has to be 1. So that this formula, which works for most things, works in all the cases we need it to. So 0 factorial does in fact equal 1, so that the number of ways of picking 10 things out of 10 things is only one way. Okay, here's a weirder question. In this group of 6 people, how many ways can I pick none of us?
No, choose none of us.
It would also be 1.
Wow, it choose like 6 random people, so that it's one possibility of them choosing 6 random people.
Right? Well, no, it's really that I'm choosing nobody. I'm picking in this group of 6,
Yeah.
I'm going to make a group of nobody, and there's one way of doing that. There's nobody in my group. How many ways can I pick? How many ways can I pick one person? By the way, there's 5 of us, not 6 of us. I'm sorry. Sorry, apologies. There's a hidden person over here. How many ways can I pick one of us?
5.
Right, 5 choose 1 is 5. How many ways can I pick 2 of us? 5 choose 2 is 10. Me and you, me and you, me and you, me and you. You and you, you and you, you and you. You and you, you and you, you and you, you and you. 10 ways. Now here's the fun part. 5 choose 3 is also 10. 5 choose 4. So if I said how many ways can I pick 4 of us? Well, I'm going to pick not me or not you or not you or not you or not you. So the number of ways of picking 4 of us is the same as the number of ways of picking not one of us. And we already knew how many ways there were picking one of us. There were 5 ways. Me, you, or you. So the nice thing here is that there's symmetry. The number of ways of picking one person out of a group of 5 is equal to the number of ways of picking 4 people out of a group of 5. Because you're just picking the person to exclude instead of the person to include.